Hey guys, welcome to Metamorphic Rocks Part 2. Today we're actually going to work with the different types of metamorphic rocks. We're going to talk about the textures and how we tell them apart. So it's really important that for this one you have your reference tables ready to go. Make sure you're open to page 7. We're going to be talking about them a lot. You're going to see this picture come up a lot during your video lesson today. Alright guys, so make sure you're doing this. Make sure you're taking notes on this. And let's go! Alright, so just like with other rocks, we're going to talk about textures. So when we're talking about metamorphic textures are broken into two types. We have what we call foliated and non-foliated. Remember, we talked about this. This means that the minerals themselves start to line up and start to organize themselves based on their density and other various properties. Now, some rocks are foliated, which means the minerals start to line up, they start to organize themselves, and some metamorphic rocks are not. Okay, so when you're looking at the reference table, you will see this. So if we're here on page 7 of your reference table, and you can see the scheme for the metamorphic rock identification. So when we look at this chart, you'll see you've got the texture here, which is what we just talked about. So you've got foliated and you've got non-foliated here. Okay, and then you've got grain size, which is the size of the particles, the crystals inside. So you've got fine grain, which means they're really small, you can't see them with the naked eye. Fine to medium, which means they're getting bigger, and then medium to coarse, coarse being that you can see them nice and big. You see the process repeats again here. The composition here, okay, this is an important one to pay attention, so I'll zoom in on this a little bit. Okay, if you look here, okay, these are the different possible minerals that could be inside any of the rocks that are named over here. We'll go through that in a minute. But when you're looking at this, you see you got mica, quartz, feldspar, amphibole, garnet, pyroxene. We've talked about all these, but it's really important that you pay attention. See how mica is all the way here? That means all of these rocks could have mica in it. But you have this rock up here. You see how it doesn't have anything else in it? That means this rock is going to be made almost exclusively of mica. Now all the other guys, these three guys down here, okay, can have mica, but then they can also have all these other guys in it. Can you not see a test question, a Regents question that comes from that? The other thing you want to notice is the pyroxene down here. Pyroxene is only going to be found in schist or gneiss. You're never going to find it in phyllite or slate. So that's a really important thing to happen. The type of metamorphism, okay? All these rocks on this top part of the chart up here are going to form through, sorry, the book is being kind of a pain, but regional metamorphism, okay? What does that mean? This is plates slamming into each other, mountains forming, plates subducting under the other, things like that, okay? And as you get deeper and deeper, the heat and the pressure is going to increase. So this would be formed by the mildest form of regional metamorphism, which means you're really far away from where the plates are slamming into each other. And as you work your way down, these guys are closer and closer and closer to the actual point where the continents or where the plates are striking each other. So gneiss is going to happen right where the continents or the plates are hitting each other. The most intense heat, the most intense pressure is also going to happen at the deepest part, whereas something like slate is going to happen much further away and where the heat and pressure isn't nearly as much. Okay, here you have comments about each one. We're going to go through these rocks and describe them. Here you have the rock names, okay, working all the way down. And then you have the map symbols. Now, you guys saw in the last test, these map symbols are important. You need to be able to use them. You need to be able to understand which one represents what. There's the map symbols for the sedimentary up there too. You're going to be responsible for knowing all these different map symbols. If we look at the bottom of the chart, it's very similar. Okay, you got the non-foliated texture. Okay, which means the minerals are not aligned. You see how it says mineral alignment up here for foliated? That means the minerals are lined up. And then sometimes they get so extreme that we call what we call banding. We'll see that in a couple minutes in the rest of the video. These guys, you don't have any of that stuff. Once again, you have grain size. Okay, the composition is variable for this guy. This guy is almost exclusively quartz. This lady, or non-gender specific, sorry, I gotta stop using all those pronouns, is made out of calcite and dolomite. And this is various minerals again in particles and matrix. Okay, this one up here is created by contact metamorphism, heat. This rock, is the only metamorphic rock that is only caused by contact metamorphism. The other three non-foliateds can be caused by regional or contact metamorphism. Really important, could show up on a test or a quiz. Okay, and then right here, once again, you've got your comments about them. You've got the names of the different metamorphic rocks, and you've got the symbols. Really, really, really important that you guys know this chart. So the first rock we're going to talk about is slate. Slate is an example of a fine grain, foliated regionally metamorphic rock. Okay, it is mostly made out of mica. If you remember mica were those minerals that were like pieces of plastic. They look like they peeled away really easy. That's going to be important in a second. It's an example of low-grade regional metamorphism. What does that mean? It means that this process happened far away from the actual contact point between the plates, okay? But there was enough heat and energy to change it, okay? It's foliated, which means the mica inside of this has started to align itself in a certain way, okay? It was a rock like shale or mudstone or siltstone that had a lot of mica in it. Since it had so much mica in it, one of the identifying characteristics of slate is that it has this excellent cleavage. Remember, cleavage is how it breaks. It always breaks the same way. If you look at a sample of slate, you may actually have this like on your roof or places like that. It tends to be very flat. It tends to be very smooth. In fact, we tend to use it for things like chalkboards, or we used to use it a lot for chalkboards. So if you think of the school boards in class that are black, those used to be made all out of slate. Or green, those were all slate. Or red, those were all slate. Slate can be lots of different colors depending on what minerals are inside of it. So if you're looking at the rock in front of you right now, this is an example of slate. You can see how it's very smooth. Okay, you can't clearly see any crystals inside of it, but this would be an example of slate. The second picture that you're looking at is actually a slate mine. Okay, this is them pulling slate out of the ground, and you can see it's these big flat tablets, very smooth. They all break the same way in this one directional cleavage. Why? Because of the mica. Since it always breaks this way, it's actually incredibly useful for things like blackboards, like we said. Some older roofs will have shingles made out of this, but the most common use is in this. This is a pool table. Pool tables, especially well-built ones that are very expensive, tend to have slate as their base. The green felt that goes on top, that's different. But the board itself tends to be made out of slate. Why? Because it's a rock. It's durable. Okay? This is not going to break like cheap ones that are made out of wood. This is going to maintain its normal flatness for a very long period of time. They're a bit more expensive, one, because they're heavy, two, they're harder to make, but they last longer. Cheap pool tables have a wood base. This one has a nice slate base, so it's nice and strong and durable. Here we have an actual sample of slate. So you can see it is smooth, very, very, very smooth. Okay, if you look closely enough, there you go. You can actually see the layers inside of it. You can see how this would break along those thin layers and give you lots and lots of flat, smooth surfaces. Here you can actually see the chunks of mica themselves. You've got some bigger crystals there, but you see the shininess of it. So this very smooth sample would be an example of slate. So the second rock that we're going to talk about on the metamorphic chart is phyllite. Phyllite is still fine grained, but the crystals are a little bit bigger. It forms under slightly higher temperatures and pressures than slate. Okay, the parent rocks are roughly the same: shale, mudstone, and siltstone. Okay, it's got a lot of muscovite and a lot of chlorite, which are the minerals that are inside of it. And one of the things that happens is it tends to get much more of a sheen, a glossy, almost aluminum foilish kind of color in it. You can actually see it. It's the second one listed on your chart. Okay, and if you're looking at it, you can see it's right here. Okay, it's foliated. Okay, you can see the minerals that are in it, and once again, you can see the symbol at the end that identifies phyllite as this on a map. Now, the picture that you're looking at in front of you right now is an actual sample of phyllite. I don't have one on me, unfortunately, so we'll talk about this picture, but you can see it does kind of have that shininess. It almost looks like it's wrapped in aluminum foil. Okay, you can start to see the wavy appearance in it, but you can't quite see the mineral layers or the foliation, but it is there. So the next rock we're going to talk about is incredibly important. It's what we call schist. I said schist. I kept it clean. Okay, so schist is an incredibly common metamorphic rock. Okay, it is medium to coarse grained, which means we can actually start to see the crystals in this. It comes from the same thing: shale, mudstone, but you can also include basalt and sandstone and limestone. It's going to have lots and lots of mica, which is going to give it a shine, but it's also going to have other minerals in it. Lots of garnet, amphiboles, maybe even some pyroxene. Okay, we find a lot of it actually here in New York. The bedrock of New York, particularly Manhattan, is made out of a type of schist that we call Manhattan schist. That's what makes Manhattan such a good place to build large skyscrapers, because the schist is an incredibly tough and durable rock that's very hard to dig through, but once you anchor a building to it, it's incredibly strong. Now, if we're looking at the reference table shows us schist. Okay, and we can see it here. Once again, it's foliated. You can see it has the minerals aligned. You can see the minerals that are in it. And if you look all the way at the end, once again, you can see the symbol, the map symbol for schist. Now, when we're looking at the pictures, you can see here we have a picture of actual schist. You can see the shininess. It looks very different. Almost looks like a ball of aluminum foil, but this is an actual rock. Okay, and we find it. Here's a picture of it actually in New York. This is if you've ever driven up towards the George Washington Bridge and you look to the right-hand side right before you go to Jersey, you will actually see this. This is a solid chunk of bedrock, the crust that actually uplifted between these two buildings while it was there before the buildings, and it was just too expensive and too hard to knock down and drill through, so they just kind of left it there. And it's been there for time immemorial, and it'll still be there. You could drive by it today. You've also seen this if you've ever gone to Central Park. You've ever climbed on those rocks when you were a kid with your parents and stuff like that. Those rocks you were climbing on were actually an example of Manhattan schist.
Example of actual schist. Okay, you can see the microcrystals. They make it really, really shiny. You can see how brilliant it is. Okay, you can start to see how the dark and light minerals are starting to kind of organize themselves. They're starting to foliate themselves. They haven't quite gotten to the best lining yet. But this is an example of actual schist. I said schist.
The last of the regionally formed metamorphic rocks is what we call gneiss. This is how this word is pronounced. I know it's got a G in front of it, but it is pronounced gneiss. Gneiss is a coarse-grained metamorphic rock. It forms at extremely high temperatures and great depth, and it can form from just about any type of rock, examples being shale, sandstone, and any igneous rock. The interesting thing about gneiss is that you get this thing called banding. Banding happens when the minerals get segregated. Now, what do we mean by segregated? We've talked about this in lots of classes. Things get separated into dark and light. Okay? It's nothing to do with racism, just dark and light minerals. Okay? And so what ends up happening is you get these bands that go around, but they're not the same as a sedimentary rock. In a sedimentary rock, the lines, the layers are continuous, which means they wrap around the whole thing. In this, they're kind of cut off and spotty. They don't go exactly the same way. The other thing about gneiss is usually going to show you evidence of directed pressure. What does that mean? That means the minerals are going to get compressed, squished, where the pressure was applied, and stretch out, elongate, where the pressure wasn't, perpendicular to it. We talked about this the other day. Okay, so if you're looking at the background of all these pictures, you can see this. We find gneiss actually, once again, here in New York. Okay, up towards the university called Fordham in the Bronx. Okay, you find what we call Fordham gneiss. Okay, and once again, it's a good building stone. Now, if you're looking at the reference table here, you can see gneiss. It is a foliated metamorphic texture showing banding. The minerals are medium to coarse in terms of crystal size. You can see all the minerals that are in there. It's an example of extreme high-end regional metamorphism. And if you look all the way towards the end, you can see the map symbol for this. So if you're looking here, you can actually see a sample of gneiss. You can see the clear-cut banding. Okay, like I said, sometimes this rock gets put under a whole lot of pressure. So in the picture that you see right now, you can actually see the waviness and the twistedness. And in the picture you're looking at now, you actually have a sample of the Fordham gneiss up in the Hudson River. You see that big C, that's Fort Columbia University. The rowing team painted it there, and that would be an example of actual gneiss in our city. So that does it for the first part of the chart. Once again, what did I do? I talked too much. I've done it all year, let's be honest. So I'm going to finish the second part of the chart in the second video. They're both your responsibilities to watch. So make sure you watch part 3, I guess, of Metamorphic Rocks. And I'll see you in a minute.